welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 7, Lesson Number 4, Factoring Based on Conjugate Pairs. Before we begin, let me remind you that you can find a worksheet and a homework assignment that go with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes at the top of every worksheet. Use your smartphone or a tablet to scan that code, and you'll be brought right to the video that's associated with that lesson. Okay, let's begin. So, conjugate pairs are binomial pairs that have exactly the same two terms, but differ in whether those terms are added or subtracted. Conjugate pairs are very, very important in mathematics, and they're going to come up a lot in this course and in Algebra 2. For instance, you can have something simple like x plus 3 and x minus 3, the same two terms, x and 3, but one of them is being added, one of them is being subtracted. You could have a little bit more complicated, 2x plus 7, 2x minus 7. Simple enough, right? Or you could have something like 2 minus y and 2 plus y. There's no need for the variable to come first in the conjugate pair, and it often doesn't. Finally, you could even have more than one variable, like 5x minus 3y and 5x plus 3y. All right, all of these are examples of conjugate pairs, and if you kind of hone in on that last one, right, here are those two terms, right, 5x and 5x, and 3y and 3y, but one of them is being subtracted and one of them is being added. All right. Conjugate pairs make up a very interesting relationship in mathematics because of their products. So what we're going to really do in the first half of this lesson is just investigate what happens when you multiply two conjugates together. All right, I'm going to clear out that little bit of text, and we're going to jump right into that. Here we go. All right, find each of the following products of conjugate pairs. See if you can work out a pattern. Now, we've done a lot of products lately. In fact, in Lesson 2 of Unit 7, that's all we did, right, was multiplying polynomials. So we should be pretty good at this, but let's do the first one together. We could FOIL, we could go with double distribution, we could use the box, I don't care. Let me do double distribution just for a second. I'm going to take that x and I'm going to multiply it by x minus 5. And then I'm going to take that positive 5 and I'm going to multiply it by x minus 5. All right, so I distributed this and I distributed this. So now when I multiply this x through, I get x times x, which is x squared, and x times negative 5, which is negative 5x. Now when I distribute this 5 through, I get a positive 5x, and I get negative 25. Now notice, a negative 5x and a positive 5x, they're opposites of each other. Just like when we did the method of elimination back when we were solving systems of linear equations, I know that was a little while ago, those two terms are going to cancel. They're going to give us 0x, so we're not going to even write it. And in fact, we're just going to have x squared minus 25. All right, it's really kind of cool. Now what I'd like you to do is do the same thing in B and C. Pause the video for a moment and work out letter B and C and see what you get when you multiply those conjugate pairs together. All right, let's go through them. Hopefully you found something worked out almost identical. Maybe in this next method I'll review how to FOIL, okay? We do first x times x, which is x squared, outer, x times 2, positive 2x, inner, negative 2 times x, which is negative 2x, and last, negative 2 times positive 2 is negative 4. These two terms are again opposite, so they cancel, and we just get x squared minus 4. All right, maybe this one, I'll go with that box multiplication method. Choose your pick. Pick your choice, whatever. 4x plus 1, 4x minus 1. You think I could have made the box a little bit bigger. 4x times 4x is 16x squared. 4x times negative 1 is negative 4x. 4x times positive 1 is positive 4x, and positive 1 times negative 1 is negative 1. Remember, along the diagonal, they're almost always your like terms. So those two, again, are opposite, they cancel, and all we have is 16x squared minus 1. right? In each case, those two linear terms are canceling each other out, okay? Now letters D, E, and F, they seem a bit more complicated, but the same pattern is going to hold true. In fact, letter D is about the most generic that you can possibly get. Let's go back to foiling, right? We get x times x, which is x squared. That's my first. We get x times negative y, which would be negative xy. That's my outer. Now here we've got y times x, but keep in mind that y times x and x times y are the same thing because of the commutative property of multiplication. So I'm just going to write that down. And then my last, y times negative y, would be negative y squared. These two are again opposites and they cancel, and we get x squared minus y squared. Okay? I would like you to do letter E and letter F and do the full-on multiplication. Even though you might think that you see the pattern, and that's great, please multiply them all the way out. Okay? All right. Let's work through it. I'm going to continue to just do some foiling. That's what most teachers do. If your teacher doesn't do it, that's not a problem. Okay? Different teachers have different philosophies on multiplying binomials. So first, 2x times 2x would be 4 times x squared. So that's our first. Our outer, 2x times negative 3 would be negative 6x. 3 times 2x would be positive 6x. And 3 times negative 3 would be negative 9. These two terms are again opposites, and we just get 4x squared minus 9. Let's do the last one. 5x times 5x is 25x squared first. 5 times negative 2 is negative 10. X times y is just, well, x times y. Then here we've got 2 times 5, which is positive 10, and y times x is the same as x times y. And then 2 times negative 2 is negative 4. Y times y is y squared. Yet again, we've got opposites here that cancel, and we just simply have 25x squared minus 4y squared. All right. Now notice in every one of these cases, essentially what we're getting is we're not getting FOIL, we're getting FL, right? FOIL is first, outer, inner, last, right? But the outer and the inner keep canceling, and we're just getting FL, right? We're just getting first and last. And in a certain sense, we're always getting first minus last, if you want to think about it that way. So let's formalize this pattern really quickly, all right? Pause the video now, write down anything you need to, and then let's take a look at the general pattern for multiplying conjugates, okay? All right, let's do it. So here we go, multiplying conjugate pairs. Now, the most generic thing that we get is a plus b times a minus b. Well, we just multiply this and this. We multiply this and this, and then we subtract, okay? Now again, this doesn't generally work except with conjugate pairs, all right? So you can definitely say something like, well, if I have 3x plus 2 times 3x minus 2, it's okay to do 3x times 3x and get 9x squared, and do 2 times negative 2 and get negative 4. That's okay. All right? But what would not be okay is if you had 3x plus 2 times 2x minus, let's say, 5. It wouldn't be okay to do 3x times 2x and get 6x squared and then do 2 times negative 5 and get negative 10. That is wrong, wrong, wrong. Okay? It must be the product of conjugate pairs. All other products you really have to do by going through the double distribution or the foiling or the boxing or whatever you want to call it. Okay? So I'm going to clear this out, and then we're going to use that pattern to quickly multiply conjugates. Okay? All right, let's do some quick conjugate multiplication. So here we go. Use the pattern from exercise 1, or from that box that we just looked at, to quickly rewrite the following products. So this is awesome, right? We have way more room than we need. So conjugate pair here says I can just do x times x and get x squared. 6 times 6 and get 36. X squared minus 36. Here we can get 5x times 5x, 25x squared, 2 times negative 2, and get negative 4. Wow, is this quick? If you think you have the pattern, pause the video now and work through the rest of these. If you've got the pattern, it should take you only a couple minutes. All right, let's work through them. Again, conjugate pairs, 2x times 2x will be 4x to the second, minus 7y times 7y, 49y to the second. All right, letter D, again, conjugate pairs, 4 times 4 is 16, x times x is x squared. Make sure that's 16x squared and not x squared minus 16. The variable comes second if it comes second in the conjugate pairs. Here we go, same thing. 6 times 6 is 36. 5y times 5y, 25y squared. Finally, 10x times 10x will be 100 x squared minus 4y times 4y, 16y squared. All right, a plus b times a minus b is a squared minus b squared. Okay, now what's cool about this is just like we did in the last lesson, we can now reverse this. And we can look for a form that looks like a squared minus b squared and factor it into the product of two conjugate pairs. That's what we're going to do next. Pause the video now. Take a look at these, compare them to your answers, and then we'll move on. All right, let's do it. All right, write each of the following first in the form a squared minus b squared, and then as equivalent products of conjugate pairs. In other words, we can write x squared minus 81 as x squared, that's a little silly, but I just want to show you the form, minus 9 squared, all right? But that means this must be x minus 9 times x plus 9, right? In factoring terms, this is called factoring the difference of perfect squares. Let me write that down right here. The difference of perfect squares. The technical name is factoring binomials based on conjugate pairs. But it's the difference of perfect squares. Difference meaning that it's a subtraction. Perfect squares meaning that both of these must be perfect squares, meaning that they must be written as something squared minus something squared. So take a look at B, right? We can think of 9x squared as being 3x times 3x. In other words, 3x squared. We can think of 4 as being 2 squared. So 9x squared minus 4 is the same as 3x minus 2 times 3x plus 2. Right? And again, if you don't believe me, multiply those back out and you'll get that, right? Watch out for this one, 25 minus y squared. That would be the same as 5 squared minus y squared. So that can factor into 5 minus y times 5 plus y. Be careful, don't make it into y minus 5 times y plus 5. That's not correct. All right. Now, if you think you have the pattern, pause the video now and work through D, E, and F. If you don't, hold on and we'll work through the rest of them together. All right, let's go through it. Again, the difference of perfect squares. You'll always know you have it if all the numbers are perfect squares, numbers like 1, 4, 9, 16, 25, 36, etc., and if it's subtraction. So here we go. 4x squared is the same as 2x quantity squared. 81y squared is the same as 9y quantity squared. So we can now factor this into 2x minus 9y and 2x plus 9y. That's it. Now this one might be a little bit trickier for two reasons. Number one, the number 121 is rather large, and the number 1 is rather tricky sometimes. But 121 is 11 times 11. It's 11 squared. So I can think of that first term as 11x squared, and I can think of the second term as 1 squared, because 1 times 1 is 1. So this will all factor into 11x minus 1 times 11x plus 1. By the way, I haven't pointed this out yet, but of course it's completely okay to write it like this. Pause for a minute and think about why it's okay for either one of those two to be written. All right, well, hopefully it's because you know that multiplication is commutative, and that's really what we're doing, right? We're writing down a product, and a product can be written down in any order you want. So either way is okay. Letter F, again, a little bit tricky because of the 1. The 1 can be thought of as 1 times 1, and the 4x squared can be thought of as 2x quantity squared. So, using the structure of this problem, it's 1 minus 2x times 1 plus 2x. And that's it. So now think about this. We now know really two ways to factor. They're very problem specific. One way to factor is by factoring a GCF out of a polynomial. That's what we did in the last lesson. Another way to factor is if we notice that we have something of the form a squared minus b squared, right? The difference of perfect squares. If we've got something like that, then we can factor that as the product of two conjugate pairs. Okay? So I'm going to pause the video, or I'd ask you to pause the video now, write down anything you need to, and then we'll move on. All right, let's do it. Okay, exercise 4. Let's take a look at the binomial x squared minus 9. Amelia believes that x squared minus 9 can be factored as x plus 1 times x minus 9, while her friend Isabel believes that it is factored as x minus 3 times x plus 3. Fill out the table below to develop evidence as to who is correct. Use technology on your calculator to help. All right, so it's time yet again to bring out our TI-84 Plus. Let's do it. That wasn't a very loud snap. Hopefully the TI-84 came open on that. You never know, it's trained to open and close on my snaps. So we've got our 3 columns. And what we're going to be doing now is just like we did in a previous lesson, we're going to be putting those in, but now as y1, y2, and y3. So let's start by hitting the y equals button on our calculator. Okay, now what I'd like you to do is I'd like you to clear out any equations that might be in there. Okay, give you a moment to do that. Okay, so now what we're going to do is our first expression, y squared minus 9, we're going to put in y1. Our next expression, x plus 1 times x minus 9, we're going to put in y2. And our last expression, x minus 3 times x plus 3, we're going to put in y sub 3. All right, so let's do that. Let's go up to y1. Let's put in x squared minus 9. In y2, let's put in parentheses, x plus 1, parentheses, times x minus 9, parentheses. In y3, let's put in x minus 3, parentheses, and parentheses, x plus 3, parentheses. Let me pause for a minute just to let you catch up, and maybe to let myself catch up. All right, what we definitely want to do always after we've entered things, especially multiple equations like that, is that we want to make sure that we got it right. So look at all 3 equations. Make sure that you've got your x squared minus 9 correct, your x plus 1 times x minus 9 correct, and your x minus 3 times x plus 3 correct. Now what we'd really like to see is what each one of these expressions is equal to for these 4 values of x. So what I'd like you to do is go into your table setup. Remember, it's right up here. So let's do that. Let's go into our table setup. We just want to make sure that our table starts at 0 and then it goes by 1. It may already be there because of the previous problem we did, but if not, make sure your table start is at 0 and your delta table is at 1. All right, do you have that? Okay, let's go into the table now. Remember, we get that by hitting second graph. All right, and now let's take a look at that first row of the table. When x is equal to 0, well, our original expression, which is x squared minus 9, is equal to negative 9. On the other hand, when x is equal to 0, we find that the second expression is equal to negative 9, and so is the third expression. So that doesn't help us out at all. It seems like all three might be equivalent. Maybe they are. But when we put x equals 1 in, we find that the first expression is negative 8, the second expression is negative 16, and the third expression is negative 8. Now immediately what that tells me is that the first and the second can't be equivalent because they have different values for the same value of x. But it still seems like 1 and 3 are the same. When I put x equals 2 in, I'm going to get negative 5 for the first expression in that table. I'm going to get negative 21 for the second one, further reinforcing that they are not equivalent. And I'm going to get negative 5 for the third, again, further reinforcing that these two probably are equivalent. Finally, for x equals 3, we're going to get 0 for the first expression. We're going to get negative 24 for the second expression. And we're going to get 0 for the third expression. So it seems, at least based on the evidence, that x squared minus 9 is equivalent to x minus 3 times x plus 3 because those are all the same. In fact, if we scroll a little bit more in our table, right, what we see is that that first column and that third column continue to be equal. Now, we can algebraically show that's true by simply multiplying out the two pairs of binomials. So I'd like you to do that. Take a moment and use double distribution or foiling or whatever to multiply out Amelia's answer and Isabel's answer. But pause the video now and take a moment to do that. Okay, let's go through it. Well, I think I'm just going to do a little bit of foiling. For Amelia, we've got x times x, which is x squared, that's my first. X times negative 9, negative 9x. 1 times x, positive 1x, and 1 times negative 9, negative 9. So I get x squared minus 8x minus 9. So this is equivalent to this. But for Isabel, we get x times x, which is x squared. That's my first. X times 3, positive 3x. X times negative 3, negative 3x. And negative 3 times 3, negative 9. These two are now those opposites, and they cancel, and we get x squared minus 9. All right? And what we can now see is that Isabel, by using that distribution twice, Isabel has an expression that is equivalent to where we began, right, with that x squared minus 9. All right, those two are equivalent, but not Amelia's expression. All right, I just wanted to hammer home in that last problem that what we're always doing when we factor and when we multiply two binomials together is creating equivalent expressions that are equal regardless of the values of x. Anyhow, pause the video now if you need to, write down whatever you have to, think about this problem, and then we're going to finish up the lesson. All right, here we go. So let's finish up. In today's lesson, we saw a very special type of product, and that was the product of two binomials that are conjugate pairs, identical in every way except for the addition and the subtraction. And when we multiplied two conjugate pairs, what we saw was the two linear terms, the O and the I in FOIL, if you will, cancel out and leave us only the first term minus the last term when they're multiplied out. That's a very important pattern, both for this course and for Algebra 2. So it's something that, again, you want to become fluent on in the homework tonight. For now, though, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kurt Weiler, and until next time, keep thinking,